Welcome back. In the last part of this lecture, we're going to look at some definite integrals and some applications of definite integrals. So let's start off with looking at this definite integral of e to the 1 plus 4x from 1 to 0. So I'm going to look at this and say, of course, I'm going to want to do some kind of a substitution. So I'm going to let u be 1 plus 4x. So of course du would then be 4 dx, or a quarter du is dx. And so I've got something to replace everybody, except I also need to remember that with a definite integral, I have two options. Option is I can either first do an indefinite integral on the side to find an antiderivative, then evaluate in terms of x's, or if I wanted to, I could just do my substitution in terms of u and also substitute my limits of integration to be in terms of u, and then I can just dispense with the going back in terms with x at all. And that's what I'm going to do for this one, because if we're thinking about it, it's easy enough for me to figure out what's happening with u, because with x, we know we're going from 0 to 1, and when x is 0, then u would be 1 plus 4 times 0, which would just be 1. And similarly, if x was 1, then that would mean u would be 1 plus 4 times 1, which is 5. So instead of my limits of integration going from 0 to 1, my limits of integration will be going from 1 to 5. So in terms of u now, we're going from 1 to 5. And instead of e to the 1 plus 4x, it'll be an e to the u. And instead of a dx, it'll be a 1 quarter du. And so now that I've done the substitution for everything, including my limits of integration, then it's actually a lot faster, because now I can just evaluate between u being 1 and u being 5, because those are u values, and my antiderivative is in terms of u. So I'm good to go and say that I should have 1 quarter e to the 5 minus e to the 1, or e to the 5 minus e all over 4. And that should be my definite integral. All right, let's do another one. This one is also one that's a little bit trickier. Trickier, number one, because of the notation. We need to remember that when we see that exp, that really means e to the power of. So exp 1 over x squared is the same thing as e to the power of 1 over x squared. It just is a little bit more convenient to write it that way. That way we don't have tiny little fractions inside of exponents. So I'm taking a look at this, and I see this 1 over x squared, and I also see this x cubed in the denominator. And then I'm thinking to myself, I know 1 over x squared is the same thing as x to the negative 2. And I know for x to the negative 2, its derivative would involve x to the negative 3, which would be an x cubed in the denominator. So that's making me feel like I should be using this as my substitution. I should let u be the 1 over x squared, which is the x to the negative 2. So du would be, power would come down, power would reduce by 1, dx. Or in other words, du is negative 2 over x cubed dx. I have the over x cubed and the dx, that's accounted for, not the minus 2 so much, so I would just move the minus 2 over and say that half du, negative half du rather, that's going to replace the 1 over x cubed dx. I also should be replacing my limits of integration while I'm at it. So rather than doing a little antiderivative on the side, I'm going to do it all in one go. So I need to remind myself that if x is going from 1/2 to 1, I'll figure out how u is going from what number to what number, just using my original little definition that I gave. So here x is starting off being 1/2. And if x is 1/2, then u would be 1 over a half squared. A half squared is a quarter, and 1 divided by a quarter is 4. And now for the other side of things, when x finishes up at 1, what's the value of u? Well, u would be 1 over 1 squared, which is 1 over 1, which is just 1. This is one place where this kind of approach is maybe trickier for people because the big impulse that most people will have when they start setting up their definite integral will be to put their limits of integration with a 1 in the bottom and the 4 in the top, and that actually would be quite wrong because as x is going from 1/2 to 1, u would be going from 4 to 1. 4 would be where we start and 1 would be where we end. So although that might feel a little unnatural to you right at this moment, that is exactly what we'll need to do. We'll be going from 4 to 1, and we'll be looking at our antiderivative, we'll look at our definite integral of, instead of e to the 1 over x squared, it would be e to the u. The over x cubed dx is being taken up with negative 1/2 du. And now we're ready to go. I can find my definite integral very easily because e to the u, its integral is e to the u. And I just have to evaluate e to the u going from u being 4 to u being 1. And I'll just evaluate as I always do with my top limit first. So e to the 1 minus my bottom limit, which is e to the 4. And then after I clean this up, if I were to multiply that negative and the half in, you'd have a positive e to the 4 and a minus e to the 1. So we'd have e to the 4 minus e to the 1 all over 2. Now, if you didn't like that approach, I will run through the other approach for you, which is for us to first do an indefinite integral on the side. So if we were looking at our e to the 1 over x squared all over x cubed dx, we would do the same substitution as before. U is going to be the 1 over x squared, and that du is negative 2 over x cubed dx, which would mean negative half du is the 1 over x cubed dx. So you'll notice I'm starting off with an indefinite integral. I would transform that. I'd say, well, that's the indefinite integral negative half indefinite integral of e to the u du. And now I can say, well, that's half e to the u plus c, which is same thing as half e to the 1 over x squared plus c. So now that I found an antiderivative for an indefinite integral, I can use that for the definite integral part and say, well, now if we're doing a definite integral going from 1/2 to 1, so if I'm looking at that definite integral that we started with, the e to the 1 over x squared all over x cubed, going from 1/2 to 1, I know that I just need to find any old antiderivative, and there we go, we found one. There's my antiderivative. And I would need to evaluate it going from 1/2 to 1. And if I did that, evaluating at 1 would give me negative 1/2 e to the 1 over 1 squared minus evaluating at half, which would be minus 1/2 e to the 1 over 1/2 squared, which is 1 over 1/4, which is 4. And you'll see that we get exactly the same answer as before. I'll now have, again, positive e to the 4 over 2 and a minus e to the 1 over 2. I get exactly the same answer that we had in the previous one. Just now, instead of doing it all in one go, I kind of broke it up into two steps. So either way, e to the 4 minus e over 2 happens to be our definite integral. Whichever way sort of amuses you most, that's the way for you to do it. For myself, though, for future ones, I'm going to continue doing this approach of changing my limits of integration as I go, because I think that's maybe the more efficient way to do things. And I'm going to do that here with this one. If we're taking a look at this one, though, before we can even think of doing anything with it, we're kind of in a trouble spot because if I just had an e to the x in the top, that would be fine. Or if I had just an e to the minus x in the top, that would be fine. Right now, a substitution won't really help me because if I were to let u be the stuff that's in the denominator, then I would need the derivative of that. I would need a minus e to the minus x to show up in the numerator, and I don't kind of have one there, which is a big problem. So this is another one of those places where maybe you might need to do a little bit of a rewrite. So the thing that I'm going to make a note to myself here on the side is if you had that integrand 1 over 1 plus e to the minus x, and if you multiplied everybody by e to the x, you'd get e to the x on top. You'd have 1 times e to the x. E to the negative x times e to the x would be 1. Basically, I would have transformed my integrand into that. At this point, I can see, oh, now e to the x plus 1, its derivative is e to the x. Now I do see a function and its derivative. So this is one of those things where, just like we had for trig functions, where maybe we need to rewrite things first. Well, maybe we need to rewrite things first when it comes to exponential functions as well. So I've taken my integrand and I've rewritten it. And now I'm going to think about doing my substitution, and that was going to be that u was going to replace my denominator, and that meant du would replace the numerator because the derivative of e to the x plus 1 is e to the x. So e to the x dx, that'll be replaced with du. And so now we just need to figure out what's happening for u. We know for x, it's going from 0 to natural log of 5. So what's happening to u then? Well, when x is 0, u would be e to the 0, which is 1, 1 plus 1, which is 2. So it looks like u is going to start at 2. And where is it going to end? Well, x is ending at natural log of 5. U would be e to the natural log of 5. E to the natural log of 5 would just be 5. And 5 plus 1 would be 6. So it looks like 6 is where we're ending. So now I'm going to turn this definite integral into one in terms of u's. The e to the x plus 1 in the denominator, that's now a u in the denominator. The e to the x dx, that's being replaced with du. And instead of going from 0 to natural log of 5, we are going from 2 to 6. Okay, and I'm ready to go. It's 1 over u, and I know the antiderivative for that I'll be using is natural log of u, absoluted. And in fact, I can be even lazier here. I don't even really need the absolute values because I'm going to be evaluating between 2 and 6, but it doesn't really make a difference. Either way, I'm going to wind up with natural log of 6 minus natural log of 2, which is natural log of 6 divided by 2, or in other words, natural log of 3. So turns out that this definite integral is equal to natural log of 3. We didn't graph this as a function, or we didn't even think about what this integrand would look like as a function, but it is something that is above the x-axis. So actually the number that we found here does represent an area. It's the area under this curve between 0 and natural log of 5. But now let's do a real for real area problem. The area bounded by the graph of this function, the x-axis, and the lines x equals 1 and x equals 4. I know what this is. This is an e to the x graph. It's been reflected in the y-axis. It's been shifted up by 1. So e to the x, we know what it looks like. Reflected e to the x, we know what it looks like. This is a compressed e to the x, and it's then been shifted upwards by 1. Either way, we're above the x-axis. So no matter what, I can be confident for my function that it's going to be above the x-axis. And we're looking at bounded by this curve, the x-axis, the lines x equals 1 and x equals 4. So if we're looking at this area, that is just a definite integral. Our area will be the definite integral from 1 to 4 of 1 plus e to the minus 3x. If you wanted to, I mean, you can definitely do this with a substitution if you needed to. I don't think we totally have to for this one. So for starters, the first term, x 1, when I find an antiderivative for that, it should just be x. For e to the minus 3x, for that you could, if you needed to do a substitution, I suppose you could let u be minus 3x, and you know that du would be minus 3dx, and then the minus 3 would have to be brought over. You can rationalize without too much effort to yourself that an antiderivative for e to the minus 3x should be minus a third e to the minus 3x. And that's because if we differentiated this, the minus 3 would come down, canceling out the minus 1/3. Any way you do it, that's an antiderivative for our function, and we only need to evaluate between 1 and 4. So away we go. We'll evaluate, and then we'll know what our area is. Evaluating at 4, I'd have 4 minus a third e to the negative 12. And then evaluating it at 1, I'd have 1 minus a third e to the negative 3. And then there's not really much else that I'll be able to do to clean up after that, or not much that I really want to do to be able to clean up after that. I could combine the 4 and the 1. 4 minus 1 is 3. I have minus 1/3 e to the negative 12, or 1 over 3 e to the 12. And then I've got a minus negative, or a plus 1/3 e to the minus 3, or a plus 1 over 3 e to the 3. If I really felt like it, I suppose I could make common denominators and combine everybody together. But since I'm looking for an area, if I really desperately needed to know this as a decimal number, I could, or I could just leave this as a reasonable enough answer for what my exact value is. Okay, last one for us to tackle is a differential equation. And I've got a differential equation now involving exponential functions. And for this, I have my second derivative. And I've got two initial values, one for what the y of 0 is, and one for what y prime of 0 is. So y prime, or in other words, the first derivative, I'd find that by integrating that second derivative with respect to x, and that second derivative is e to the x plus e to the minus x. And I know that my y prime will be one of these antiderivatives. So an antiderivative for e to the x is e to the x. For e to the minus x, an antiderivative is negative e to the minus x. And of course, that's because derivative of minus e to the minus x would be positive e to the minus x. The negative would come down. And then, of course, plus constant c1, my first constant for solving. I know that y prime is of that form, and I also know y prime happens to pass through the point 0, 0. So using y prime of 0 equals 0, I could say, well, 0 should be equal to e to the 0 minus e to the 0 plus constant 1. E to the 0 is 1, and e to the 0 is also 1. And so we wind up finding that constant c1 is 0. So now we can say, good for us, we now know what y prime is. Y prime is e to the x minus e to the negative x, and there is no plus anything at the end because the constant at the end is 0. Okay, so now let's go backwards one step further and find out what y is. And so for that, I will need to, on the side, do some more integrating. And so now for y should be one of the antiderivatives of y prime. In other words, it should be one of the antiderivatives of what we just found, e to the x minus e to the negative x dx. E to the x, its antiderivative is e to the x. E to the negative x is a negative e to the negative x, which will combine with the other negative to give me a positive. And then there'd be another constant of integration that would pop on up. And then again, we've got one last little point to deal with, which is we know y of 0 should be equal to 3. So 3 would be the y value when x is 0. And so we have e to the 0, e to the 0, and c2. So I find that my constant c2 looks like it is actually 1 which means now we have our solution to our differential equation. Our function is e to the x plus e to the negative x plus 1.